For number 3, we saw that the signal was down converted via undersampling to an Alice spectrum of 80 megahertz. The bandwidth is retained, so we have our signal from 60 to 100 with a center frequency of 80. Now, and then we figured out that the actual sampling rate, the best sampling rate that we should get is actually, that we should do is 62.22 megahertz instead of 60. So if that was the case, we would need to down convert this like so. So again, we have the same signal. This is 140. And if I am down converting this, this would be at, let me try to get rid of this first so I have more space. Okay, so this is going to be down converted and produce an Alice spectrum. So 140 minus 62.22 will give me, let me use my calculator, 140 minus 62.22 is 77.78 megahertz. And this is 77.78 megahertz. Now, is this situated in the first Nyquist zone or not? So to determine the Nyquist zones, remember that we actually have to divide the sampling frequency by half. So if our Fs is 62.22, the first Nyquist zone will be 62.22 divided by 2. Which is at 31.1. So from 0 to 31.1 is the first Nyquist zone. So obviously this does not fulfill the first Nyquist zone, which means that we need to further down convert this. So let's do that. So let me try to select this, so we have more space right here. Okay, move over here. Okay, maybe make this a bit smaller, like that. And then like this, move it here. Okay, so now I have more space. Let's try to draw this. So down converting again. So 77 minus 77.78 minus 62.22 will give me something at 15.56. Does this fulfill the first Nyquist zone? I think so, because this is the range of the first Nyquist zone. Okay, so let me try to highlight the first Nyquist zone. It extends from here to here, and this is 31.11 megahertz. So 31.11, and if we want our signal to be centered at the first Nyquist zone, this should be between 0 to 31.1 divided by 2. So 31.11 divided by 2 is actually 15.55. This is the center of the first Nyquist zone, which means that we got it right. But our bandwidth is actually plus minus 20, right? Which is quite kind of big. So if this is plus 20, this will end up extending beyond the first Nyquist zone, because 20 plus 15.56 will give me 35.56, and 15 minus 15.56 minus 20 will give me something that is minus 4.44. So it extends outside of the first Nyquist zone, but the center frequency is situated perfectly centered in the first Nyquist zone. So I guess that's okay for us, because we are using an approximation based on the formula. Okay, so I hope everyone understands the difference between number 4 and number 3. Number 3, they give us the Nyquist rate, 60. And then we found out that it is down converted into this. But when we are finding the desired sampling rate, we actually want to down convert up until the first Nyquist zone. Okay? Moving on. Of course, you can also do the aliasing many times until you reach the first Nyquist zone, even for number 3. So both are applicable, but for the answer scheme, they just down converted once because they just wanted to show you that let's just do it. 80 minus 60 will give me an alias at 20 megahertz. It's still within the first Nyquist zone, but it's not centered. Okay, so still applicable, but not the best. Okay, moving on to the second example, the last example for the class today. The voltage range of an A to D converter that uses a 14-bit numbers is minus 6 volt to plus 6 volt. Find the number of discrete levels that are represented. So that is easy. 2 to the power of n, where n is 14. So this is 2 to the power of n. Let me use my trusty phone calculator. 2 to the power of... Wait, I don't think I know how to use this. Okay, so the answer is 16,384 levels. So for B, the number of voltage increments is basically 2 to the n minus 1. 16,384 minus 1. 16,383. Easy. Number 6. Or 6. Number 6. C. Example 2C. I don't know why. It's very hard for me to talk in cold weather. I'm just struggling. So C. The resolution of the digitization expressed as the smallest voltage increment. So we have from 6 volt to minus 6 volt, right? So the range is 12 volt. So it's asking if we digitize this range to 16.304 increments into 16,383 increments, what is the value for each increment? So basically it's just 12 volt divided by 16,383, and this would give you 732.5 microvolt. So if I have an analog signal, I'm digitizing it, each level corresponds to 732.5 microvolt. Okay, so that is all for today's class. This is actually the last lecture, but I have promised that I will give you some questions to work with for the final exam. So we will also do that. So thank you everyone for staying with me during these 13 weeks. I am sorry for any mistakes that I have done in class or if I have joked too much. I really enjoyed teaching you guys and getting to know each and every one of you. And I look forward to seeing you during the finals. And do your best, study well, don't be lazy. We will talk more and we will talk soon when I assign the questions later. Take care everyone, bye-bye.